let's talk about some basic set operations. So our basic set of operations are going to be unions and intersections and complements. We'll eventually add to that with our metric space ideas, but just some fundamentals here without anything besides just elements of sets. So a set X is a set of elements, and we say X, little x, is an element of X if it belongs to the set. So that's just the statement. X is an element of X. Some other notation, set builder notation. So if I have a set and I want to build like a subset, so I can take X is an element of R, and then I have sort of a restriction, say X is less than 2. So this is going to be set builder notation. And I'll add some color here. This first part is what type of elements we're dealing with. A lot of times it's just going to be implied that it's numbers. Here we just have numbers. If I had like r squared up there, then these would be points or vectors. And then the other part of this notation, which comes after the vertical bar, this is the restriction on the elements. Okay, so this set here on a number line, this set would just look like everything that's less than 2, strictly less than 2. So I would have an open interval from -2 to infinity, or -infinity to +2. Okay. So that's kind of some of our basic set notation. We have operations now. The first thing we're going to do is we're going to talk about unions. So unions are an operation on 2 or more sets, and it's just combining the sets into a single set. So A union B, it's the set of, say, X. It's implied that X is an element of whatever A and B are subsets of. X, such that X is in A, or X is in B. Okay, not and would mean that it would have to be in both of them, right? Or means it can be in either one. So if I want to bring these things together, well, it can either have A's qualities or it could have B's qualities, and I want to take both of those things into consideration. So it could have both A's qualities and B's qualities, but that will still belong to the union. Venn diagrams are a good way to denote these. So we draw a box for the universe. So this is our universe here. Maybe X is the universe. A is a subset of that universe, so we'll denote that by drawing a circle for A. Everything inside that circle has A's qualities. Everything inside this circle has B's qualities. The stuff that has both qualities would be, or sorry, not that has both qualities, that has A's qualities or B's qualities is the union, and that's going to be anything that's in either circle. This is A union B. Okay. I don't have to stop at just 2 sets. So we could take, say, let's index our sets A, And let's say A is going to be the set negative infinity to I. Okay, so this is an interval from negative infinity up to I. A is going to be a subset of the reals. This is a subset of R. And that's going to be what our sets are. What is the union from I equals 1 to 10 of A sub I? So like sigma notation, we can write from I equals 1 to 10. Well, this would be A1 union A2 union up through A10 on a number line. Let's kind of draw these out, at least a couple of them. So A1 is everything that's less than 1, so let's call that a 1. And I've got that stuff. A2, start at 2, and I've got an open interval there. That's that stuff. Eventually, I'll get up to 9, and I'll have the open interval from 9 on down. And the last one I need to include is at 10, and I'll have the open interval from 10 on down. The union is anything that's in any of these sets. Well, I need the things that have any color at all to them. That's just A10, since 10 is the biggest one and each of the other ones are contained in it. This union, I equals 1 to 10, AI equals the interval from negative infinity up until 10, which is our union. Okay, I don't have to have just a finite union, right? AI can be any real number. I could take I to be any real number that I wanted. Let's say AI, it's still the same thing. It's the set X is a real number such that X is less than I. Okay, so let's look at the union that I is in, say, the interval from 0 to 1, open interval, AI. Okay, so on my number line, I've got the set that starts at, I can't start at 0, right? But I can start just a little bit above 0. So any of these things are in there. And I've got open intervals all the way getting close to 0 there. And 1 on the other side, I've got this guy, I've got this guy, all of these things that are getting really close to 1, but not quite to 1, those are all going to be in there. If I take the union of all of them, that'd be anything that's in any of these. This is going to be negative infinity up until 1, because any number in here belongs to one of these a sub i's. If it's a little bit less than 1, it belongs to the AI, which is a little bit less than 1 as well. Not the same little bit less than, but just a little bit to the right. So if I zoom in there, so let's say here's 1. If I want to know that this point, say X, is in the union AI, I, and 0, 1, I'm going to take the, let's say this is 1 plus X over 2, the average of X and 1, that's going to be halfway there. A sub 1 plus X over 2 contains X. So X is in this union because it's in this specific guy, which is in this index. Okay, that was a bit technical, but we can do things with these indexes that way on unions of sets. We can take finite unions or uncountably infinite unions, or, for example, we can also take countable unions, say I is in N, AI, this is just going to be all of the reals, which, because every interval starts going one to the right farther. Eventually, no single interval is all of the reals, but these intervals just keep going forever, and I eventually cover everything. Okay, so that's unions. We can do the same thing with intersections. Intersections are slightly harder to work with. Unions just bring everything together. Intersections, the requirement is you have to have every single condition satisfied. So the intersections A intersect B, this is the stuff X, such that X is in A. So let me use my notation there. X is in A and X is in B. So intersections require both things to be true. Okay. So our Venn diagram, we've got X again. Here's our set A. Here's our set B. The stuff that belongs to both of them is that stuff, right? Okay. Let's look at some of these intersections again. So the intersection, we'll take AI equals negative infinity up until I again. So I can be any real number I wanted. The first thing that we did was I equals 1 to 10. So our picture, we had 10, we had 9, we had 2, we had 1. The intersection of all of these things, well, I've got the red numbers, got orange numbers, I've got gold numbers, I've got yellow numbers. The intersection is the stuff that is all of these colors. So this stuff right here up until 1 has all the colors. So our intersection is going to be only the stuff that is all of the colors. Right? These guys aren't in A9, right? These guys here, not in A9. These guys here, not in A2, not in A1. These guys, not in A1. So the only thing that's in all of them is the stuff that's less than 1. So this is negative infinity up until 1. Okay, let's look at the intersection for I in 0, 1 AI. Okay, what do we have for that intersection? Well, let's draw our number line here again. Here's 0, here's 1. I've got all kinds of different colors. I've got this guy. I've got this guy. I've got this guy. Right. Every point on here gets a different color. I've got, say, maybe pink's right there. Right. I need the thing that has all of the colors no matter where in this interval I draw everything. Well, if I zoom in on 0, 0 is definitely itself going to have all of the colors, but if I go a little bit bigger than 0, there's going to be an interval in there that doesn't have all the colors, right? So if I zoom in on 0, if I look just a little bit to the right of 0, this guy doesn't have the colors from here on down. If I go a little bit right yet, this guy doesn't have these colors. This guy doesn't have those colors, and so on. So the only thing that has all of the colors, the intersection, is going to be 0 does have all the colors. It's in all of those intervals, and everything less than 0 has all the colors. Anything bigger than 0 doesn't. So the intersection for I in 0, 1 of the a sub i's is equal to negative infinity to 0 with a closed bar, right? 0's in there. Things bigger than 0 are not in there. So intersections get a little trickier. Intersections, infinite intersections of open intervals might not be open anymore. Unions, infinite unions of open things are still going to be open. The last thing of basic sets that I want to talk about is complements. So if you think about complementary angles, complementary angle, it's the stuff that you need to add to an angle to make it 90. So it's kind of what's the angle missing. Complementary sets are what's missing from that set. So if E is a subset of X, E complement is the rest of X. So if this is X and this is E, E complement is all the stuff outside there. So set notation wise, E complement is equal to the set of X and X such that X is not in E. Okay. We'll call that good. For now, we'll talk about some metric space definitions and how we figure out how things are close to each other or far from each other or between two sets using using some metric space definitions. All right.